All right, good morning, everybody. So we're here to talk to you about the next generation of CPO systems design. So it's going to be more focused on the system, less on the optics, just to kind of set the stage. Do we have a clicker? Oh, here we go. But before we begin, just a standard boilerplate on forward-looking statements. So what we're showing here can refer to future plans. Just keep that in mind. We'll briefly talk about the benefits of co-packaged optics that we see. I think there's been a lot of discussion on that lately over the past several months. We'll give you a description of the system that we're showcasing today on our show floor, both in the Jabil booth and the Marvell booth. We'll talk a little bit about the form factor, give you some highlights on the block diagram, the components, the cooling solutions, the power, and of course, some software discussion. We'll also give a brief discussion on the lessons that we learned putting together this system. This was a fairly challenging system design. I mean, it wasn't easy to do, and I think there's some benefit for all of us to learn from that experience. And then we'll follow with the call to action. All right, so let's get started. So CPO benefits. So it goes without saying, most pluggable solutions today, you're going to see some integrated circuit on a substrate driving from a SerDes down through the BGA ball out of a PCB and up to a transceiver cage into a DSP. So there are quite a few components in this channel. Now, to be clear, we still think there is a market for pluggable transceivers for certain applications. But in other applications, there are distinct advantages of going to CPO, right? On the bottom, you'll see an equivalent CPO channel where you see an IC, a substrate, or maybe an interposer in some cases, with co-packaging of the optical engine. So the SerDes is driving the optics directly. The SerDes would have the DSP with the equalizer, and you can go do your electrical and optical conversion directly on package and bring fiber out to the front panel. So this results in lower power, lower latency, fewer components, right? So I think many of our peers have talked about the same advantages, but these are real advantages from a perspective of CPO. So the switch that we are talking about today is a base product specification by Marvell and Jabil's collaboration. There are block diagrams, mechanical specifications, thermal specs, and power specs, right? We will also have software support, especially on the optics management, that we're currently working on, but that will come at a later time. And as we go into the switch, you can see here, we followed the Open Rack V3 standard, right? We wanted to keep it to a standard specification, mainly ORV3. This is a 1OU design utilizing the Teralink switch family and the previously announced Marvell 6.4T optical engine, right? The design is capable of up to 100 terabits per second front panel bandwidth, and we are packing 16 ELSs and 64 Senko SNMT connectors on the front plate. To route the fiber within the tray, we're using a midboard connector approach. This is mainly to support better, mainly for manufacturability and modular design. So we can design the mainboard PCB and the ELS PCB independently and connect things independently. So if we have a yield fallout, we don't have to throw away a system. Liquid and air cooled. In our next generation, we're looking at fully liquid cooled. But liquid cooling, I think, as everyone has been saying, is going to be extremely important, even for CPO, not just for power considerations, but also for density, right? We were trying to make a very, very high bandwidth system in a very small form factor. So liquid cooling is a must. Just to wrap it up, we are also using a COM-E from Portwell for x86. This is for the control plane in this case for the switch, as well as an optional BMC. So if you're intending to deploy and you use out-of-band management, there will be a BMC option. So here's just a pictorial of that system we described, just to give you a high-level view of what it looks like. And we do have some pictures that we'll showcase later. And I encourage everyone, if you haven't been to the Marvell or Jabil booths, please stop by and take a look. We're showcasing the actual box there. So as we said, the SNs will be on the front, the ELSs are on the front, and this system has a provision for DC bus bar, but right now we're showcasing with AC power, mainly just for desktop evaluation. But of course, we can add the DC if need be. And very impressive cold plate. So hand it to Jason here.
So a little bit about how we went into this from the system design. As we look at co-packaged optics, we truly believe it's not a matter of if, it's a matter of when. And when it hits, like everything else driven by AI, it's going to have a very fast adoption rate. So from a scale manufacturing perspective, we have to be ready to do this. And this creates that pilot vehicle to validate all the processes, to validate what it takes to actually deliver tens of thousands or hundreds of thousands of units per year versus a normal ramp that you would have seen before AI. So a couple of the key things here is that utilizing the open compute kind of mentality around DCMHS, we've built this with a modular concept in mind. And we actually started this around 2016 when we did some of our first switches. And when I get to the block diagram, I'll talk a little bit more about that. But needless to say, we think about the management, the data, and then the front I/O and the chassis. Some of the things here that are pretty critical is that we did comply to the ORV3 standard with the blind mate for the liquid cooling. As we look at liquid cooling, it's really going to depend on the environments that you choose to deploy in. There's certain environments where it's full liquid, they don't want any airflow. But what we're also seeing is a lot of hybrid environments. And when you think about keeping the lasers cool so you get good efficiency out of them, they actually have the best seat in the house. They're sitting on the cold aisle, they get the air the first, and we're able to keep them cool with air. However, if your data center is not equipped to handle air-cooled equipment, we also have cold plate capabilities to place on those as well. In this first iteration, we left them air-cooled as it's a desktop model. The second thing is, as we thought about this, we thought about it from two perspectives around manufacturability, but also what are we going to want to do in the field? Is there going to be any field maintenance or any field upgrade that happens? And so as we're thinking about that, that's why we went to this distributed mid-plane connector strategy. And it allows us flexibility in the factory to make sure that we have high yields, high manufacturing throughput. And in the field, what it means is if we damage a lens on the front panel, I don't have to take the whole thing apart. I can replace just the link that goes to the front panel. As we talk about, what did we actually do with the electronics, I would say a couple things about this. First of all, it's there's nothing to see here. It's the same as you would expect for electronics on the board. So from a management philosophy, from a how do we think about it, it's all the same. All that happened was that data plane came out of the PCBA and now it floats above it. So when we think about how do we design this, we had to go from playing 2D chess to playing 3D chess because I have to do air traffic control around where's my liquid going, where are my fibers going. And I also had to be concerned about my airflows because I'm in a hybrid environment here. As I stated, in 2016 we started this and we built sort of a universal management complex. And the idea there is that I can take all the I/O types that I need, whether it's I2C, whether I go to I3C, whether it's SPI network, whatever is required there, and I put them together and I can deploy to whatever the processor needs and whatever the surrounding sensors need. And we've used this across campus networks, across passive optical networks, and across data center networks. So this same technology, once again with the DCMHS concept, is a building block that's usable across multiple product sets. The other thing we did here is we did have to separate from a PCB perspective the ELSFP. Now we did that for two reasons. So this is the front board. When you see the picture of it, you'll see we have a main board and then we have the front board. There were two reasons we had to do this. The first one is that to fit into one OU, there's a lot of stuff that has to happen. I've got to process, I've got to get the optics out, I've got to get the heat out, and then I've got to get all my cables run. So, and there's just not a lot of space left, especially after I stand the PCB off the floor. But in the front here, to make this efficient, we had to move the PCB in the Z direction. So it was a requirement, but it also gave us this more reliability, availability, service, and manufacturability, because now I have a unit that, should you choose from a deployment perspective, could be replaced. From our perspective, from a scrap perspective in manufacturing, if something goes wrong in the manufacturing process, I don't have to do the entire main board, I can just do the front board. One thing we did do that I didn't mention on the last slide is we did upgrade to I3C. As we see the firmware requirements and the uploading, having that faster access network allows us to do firmware upgrades and so forth in a much more efficient manner. You would have noticed also some header taps, and that was, as this is the first time we've ever done this, we wanted to be able to have individual access to each one of the optical engines to be able to access them very quickly and independently. Somehow I went backwards.
Yeah.
There we go. So if you haven't been out to the floor, what you'll see on the floor is this. We've actually taken the front panel off, the front half cover off as well. Some questions we've been asked, and I'll just answer them here before you get to ask them. The first question is, well, why didn't you use a shuffle box? So with a single processor and this arrangement, it's simple enough that it's actually more cost effective and easier to build if we use breakout cables rather than a shuffle box. As these become more complex and as this technology moves into a GPU tray, there will absolutely be shuffle boxes required as I take a fiber from each one of the elements and bring them together into a single port. But in this case, it was a more expedient, lower cost methodology to do it, and it made more sense, and that's also why we did the distributed midplane. The second thing I would say on this is that we did make it so that it was as universal as possible so that we don't have a lot of unique components in it. Lowers the cost, increases availability, and allows us to provide better service to our customers and then on to you or maybe your direct customer. The last thing we'd like to jump into, and Kishore and I will tag team this one, is the lessons learned. I'll start at the beginning here with, this is not easy. The liquid cooling especially, you have to really compress the height on it, but yet retain very, very good thermal extraction. And we believe we have margin within our designs, within our technology and liquid cooling to take this forward without going to dual phase or anything exotic for at least 2 to 3 generations and probably further. The second thing is that the fiber management, this is something that, quite frankly, hasn't been done that often. We've been doing it a long time in some of our advanced supercomputing type activities with copper cables, with flyover cables. The thought process is very similar from a manufacturing standpoint. The next thing I would say for us, for the two of us, working closely together early in the design process was critical, because what I found, we didn't do much of an introduction, but I come from a systems background, and working from Kishore comes from more of a silicon background. And so as we get together and work on this, that creative tension, that creative, what are the priorities comes together. And starting that at DFM means we have the ability to change. We have the ability to make it best for everyone.
Yeah, absolutely. I would second that. DFM is a mandatory requirement. It should be a PRD requirement, right? And that's how we approach this. Because ultimately, the goal is to deploy, not to just showcase. And in order for us to consider high volume deployment, we must make this manufacturable with high yields, starting from the silicon all the way up to the system. And there's a lot of co-design that has to happen in order to support that, since this is such a tightly integrated system. So that was absolutely one of the most valuable things that we learned as a part of this process, to start that early. And last but not least, and I think this is the key call to action kind of in the next slide, this was not done by a party of 1 or 2. It was actually like 5 different companies coming together really to build this system. It takes system vendors, silicon vendors, component vendors, PCB vendors, fiber manufacturers, a whole ecosystem really to do this. And that's the most critical thing that we have learned. Like, Marvell can't do it alone, Jabil can't do it alone. We need it takes a village, right, for lack of a better word. And that's really the next step, right? We talked about this actually a few days ago in my other presentation about fiber management at rack scale. That's the next step in CPO, right? We now have proofs of concepts, and some people are shipping CPO in some levels of volume. But getting into deployment in high volume at rack scale is the next challenge, and this is the call to action that we have here for OCP. Let's come together and figure out how we do that, right? Especially on the fiber management side. And then, we are also looking at ways to contribute. So.
Yeah. And I would close with, we are ready when we get the right demand signals, and as we build out the technology, we're ready to deliver and scale.
Yeah.
So, as all of you develop your plans, we're looking forward to being able to participate in those.
Yeah. Thank you.
So, happy to take any questions.
Thank you. We have 2 minutes left for questions, so please line up by the mics, and after that, we'll go for a break. All right, I don't see any questions. So I did have a request for you guys to make a contribution to OCP on your spec. So we have a monthly call every second Monday of the month. You can present your design and contribute your spec to the committee.
Yep, absolutely.
Thank you.
Thank you.